Okay. So, we've been talking about the Z-transform, and I'm going to take one more stab at trying to justify why we're talking about the Z-transform. We'd introduced the Fourier transform, which we have found has various useful properties. It helps us understand how a system behaves in terms of different frequency, different sinusoidal components. We define the Z-transform as looks the same as the Fourier transform, the DTFT, except that we're generalizing the e to the j omega term to a z term. So now we're defining this function over the entire z-plane, but when we look at its values when we look at its values on this particular set of values of z, we get the DTFT. Okay, so it's a way of what's going on?
It's just my laptop playing your video.
Yeah, I think one of me is enough for the time being. We can get the Fourier transform from the Z transform just by looking at the particular values. And then region of convergence, okay. We have a way, if we define the Z transform like this, for certain forms of certain sequences, we can find a closed form expression for the Z transform, which has a limited region of convergence, but assuming that we're interested in the values in the region where we do have convergence, then we can have these nice closed form expressions which can give us the value anywhere on the surface. Moreover, if we have these closed form expressions, if we can express them as these rational polynomials in Z, then we can understand those polynomials in terms of their roots. And then if we have these roots on values of z for which either the numerator or the denominator of the closed form expression is 0, then we have this sort of very compact way of describing the closed form expression, which then gives us this way of visualizing and understanding the values of that closed form expression over the whole surface. So the roots of the polynomial, the zeros and the poles, are these sort of key extremal points of this surface, this magnitude surface. But if we care about the values at other points, then we just get them by saying, well, if they're close to a pole, then the value is going to get large, and if they're close to a 0, then the value is going to get small, and something in between for other values. And then, well, we said that we were interested in the values of the Z transform for z equal to j omega, which is the unit circle. So we can think about the surface. We can take this slice through the surface on the unit circle. We can unwrap it, and that gives us the DTFT, the Fourier transform. And these same considerations about, well, where are the peaks and valleys in the surface? Where are they? How close does the unit circle come to them? That gives us these peaks and valleys in the DTFT. And that's really the point, that if we can get to this closed form expression for Z transform, if we can solve it in terms of its poles and zeros, so we can sort of think of where they're going to be on the Z plane and where they are in relation to the unit circle, then we can quickly come up with an idea of what we think our DTFT is going to look like just by thinking of it as this slice of the Z transform surface. That's really the payoff. So we ended last time just by running through some of the transforms and the properties of the Z transform for the basically all parallel the properties of the DTFT, because they are a superset. In any case, in any situation, if you substitute z equal to j omega, you should get the same behavior as the same relation, same identity we had for the DTFT. Because we're talking about an entire Z surface, some of them end up looking a little bit less elegant here because we have to take these loop integrals, which is basically, the unit circle being one of the loops we can take. But they are actually the same, mathematically the same things going on. Any questions about that? All right, well, we'll follow this through. And this idea of getting to the properties of the DTFT from the features in the z-plane is sort of, what we're going to examine for the next couple of lectures. Before we get there, let's just run through an expression of using the z-transform identities to solve a problem. If we have x of n equal r to the n cosine omega 0 n times mu of n, that was actually one of the identities we had in the table. Let's just see if we can derive the identity from the table. Well, we can express this cosine as a sum of complex sinusoids, e to the j omega 0 to the n plus e to the minus j omega 0 to the n, right? That's the e to the j omega 0 to the n is the sinusoid with period omega 0, or with omega 0, frequency omega 0 radians per sample, which has got sort of the positive corkscrew, and this one's the same thing, but with a negative imaginary part, the conjugate part. So when we add them together, we get cosine omega 0. If we add an r in front here, then that's still also raised to the n, so we get the r to the n term. And then we've got we have to, I guess it's the half of that. The average of those two is the actual cosine. Then we have the mu of n here. Now we notice we've got basically some envelope times two conjugate parts. So we can express this thing as v of n plus v conjugate of n, where v of n is just one of these, half mu of n alpha to the n for alpha equal to r e to the j omega 0. But we know that the z-transform of mu of n alpha to the n for magnitude alpha smaller than, the z-transform of mu of n alpha to the n is 1 over 1 minus alpha z to the minus 1 with region of convergence z greater than the magnitude of alpha. So here alpha is this thing, r e to the j omega 0. So we have the z-transform, that's the half out here. The v of z is a half of 1 over 1 minus r e to the j omega 0, z to the minus 1, with region of convergence z, magnitude of z greater than r. Right. So now if that's v of z, and because the z-transform is linear, and the z-transform of the conjugate of something is the conjugate of the v of z conjugate, we can just write x of z as v of z plus v conjugate of z conjugate. When we work that through, well, we already had v of z as this, and then when we conjugate this twice, it ends up just flipping the sign of this exponent. You could work that through to figure out what happens, but that's how it works out, because the z part starts off conjugated, then gets conjugated again, and all that happens is we just conjugate the complex coefficient here. And so then we have, these two fractions with different coefficients down here. We end up multiplying the denominators together and summing the numerators. The half term disappears. These things sum to give us the minus 2 cos omega 0 z to the minus 1. The half makes it down to 1 cos. And then the denominator, these things are conjugates. So we get when we multiply them together, we get the sum of these two, which is just the real part, 2r cosine omega 0, and the product of these two, which is just the magnitude, r squared times z to the minus 2. So that's what that was the identity we saw, and this is just using the other identities to derive that. This, by the way, shows us that this thing is in fact the polynomial whose roots are z equal r to the j omega 0 and z equal r to the minus j omega 0, which is what we said, the conjugate pole pair at r e to the j omega 0 at radius r and plus or minus omega 0 angle. And this part is just a single 0 on the numerator at r cosine omega 0, so a real 0. Right? This thing goes to 0 when z is equal to r cosine omega 0. Okay, so we can do some manipulations in the z-transform domain using these identities. Here's another example using the slightly exotic identity that we had where we take the differentiation with respect to z. So if y of n is n plus 1 alpha to the n mu of n, so it's like alpha to the n mu of n, sort of standard geometric, right-sided geometric sequence, but it's got this n plus 1 term in for some reason. This is just this is the example we're looking at, which means that it's an exponential term with a linear growth term on top of it, right? It's growing with n, which, we notice is not time invariant function. That's okay, this is just the function here. We can express this as the sum of two things, x of n and nx of n, where we define x of n as alpha to the n mu of n, right? So that's just the 1 times alpha n plus the n times alpha n to mu of n. Well, if that's the case, then we know that the z transform of x of n is just 1 over 1 minus alpha z for z, magnitude z greater than magnitude alpha. But this one is the one that we noticed as it's in our transform pair as being the z transform of this is the derivative with respect to z of the z transform of the thing that's being multiplied by n times minus z. And so now we know what x of z is, so we can work out the derivative of x of z with respect to z, which is this. This is, we can do the derivation by parts. So d by dz of this is d by d of this fraction times d by dz of the denominator here. So d by d denominator of 1 over denominator is denominator minus 1 times denominator to the minus 2. And then d by dz of this is minus alpha what is that? Man, d by dz of this is 0. D by dz of this is minus alpha z to the minus 2. Yeah. So the minus sign gets knocked out by the minus we got from the first derivative. The z to the minus 2 gets knocked down by this to a z to the minus 1, and that's what we get. So when we add these two parts together, we have this here, we have this part down here. We see that we have to, this is the same denominator squared, so we have to multiply this. We have to put one of these on the top. So we get 1 minus alpha z to the minus 1 over 1 minus alpha z to the minus 1 squared, plus alpha z to the minus 1 over 1 minus alpha z to the minus 1 squared. So the alpha parts cancel out. We get 1 over 1 minus alpha z to the minus 1 all squared. So what's the point of going through that? So we got the answer. But the answer is a simple thing here. The z transform of this has a repeated root, right? On the z-plane, this is 2 roots at z equal alpha. So if at some point in the future someone gives us a z transform which includes a repeated root like this, we can now go straight back to what the actual function would be, right? Because otherwise it's like, who knows? We've got this repeated root. Repeated roots are a little bit tricky because they're not just 2 of these. But here's the answer. It's it's actually n plus 1 alpha to the n mu of n for a repeated root at alpha. This ties back into what we saw when we were doing the LCCDE solutions, that when we had repeated roots in the LCCDE, we ended up with an n lambda to the n, right, coming out to give us the sort of the second degree of freedom that if we were trying to solve it, we couldn't identify 2 different coefficients to do with the lambda to the n term. So we had 1 for lambda to the n, 1 for n lambda to the n, and lo and behold, here it is. If we have this repeated root, different, so far a different root, different solution, but it actually is in fact the same problem, we get this n term coming out. I wouldn't worry. If that seemed a little bit obscure, don't worry about it. Okay, so we've introduced the z-transform. We've talked about some of its properties. We've done some manipulations with it. To round out, we may need to do this problem of inverting from the z-transform. I've sort of stated that the z-transform is a unique mapping of a function into this, or a signal into this z-space. But we haven't actually gone through the process of inverting it. We could invert the DTFT. We spent some time looking at that. So let's now look at inverting the z-transform. Here's the forward z-transform again. It turns out there's no single way that's best to do this. So we'll look at 3 different ways of doing this. One is to look at how we did the inverse DTFT, and generalize that, which is the sort of the natural way to do it. Another way is to think about the fact that the z-transform is defining a polynomial in z, and just to try and work out the coefficients of that polynomial in z, which you can do by long division. The third way is basically an algebraic trick, which is to take a z-transform expression, rearrange it into the sum of simple terms, and such that simple terms are things that we can just use our identities to invert, and then we can do it just by inspection. This doesn't provide much theoretical insight, although interesting things come out of it. But it does. It's the most practical one to do by hand, should anyone ask you to invert a z-transform by hand. Okay, so here's the first version, which is thinking about the IDTFT and how we generalize that. So we said that if z if z is equal to r e to the j omega, then g of z is equal to g of r e to the j omega, which is equal to the sum over all n of g of n r to the minus n e to the minus j omega n, which is, this is sum over n times this thing is just the DTFT. So this g of z is just the DTFT of g of n r to the minus n, right? G of z on the, not the unit circle, but the radius r circle is the same as the DTFT of g of n r to the minus n. And that gets us around the problem of, like, maybe we've got a z-transform which is not convergent on the unit circle. As long as there's some circle where it's convergent, then we can set the r to some radius where it does converge, and we can still use our closed form expression. So, okay, if this is the DTFT of this, then we should be able to get this sequence back by running our IDTFT, right, which is the g of whatever times e to the plus j omega n integrated over omega, integrated over 1 2 pi cycle of omega. Right, here's our function of omega in here. Now, we've got this expression in terms of z. How can we substitute this back in? Well, we can do a change of integration variable. We can say, well, if z is equal to r e to the j omega, then d omega equals dz on jz, right? We differentiate. We take partial derivatives of both sides. This is not my strength, but I know I learned the recipe. But basically, what we're doing is this set of values of omega is a contour in the z-plane, right? If you think about what's being defined here, it's a set of values of z. So we're doing a contour integral, and then if we change dw for dz using this identity, we get this coming out. There are a few complex terms. There's a j term that comes in here. There's this thing, e to the j omega n, becomes z to the n times r to the minus n, right? So e to the j omega n is e to the j omega is z divided by r. So e to the j omega n is z to the n times r to the minus n, and then this z that comes in here, right? D omega is equal to dz on jz, so we get z to the n minus 1, and the j coming down here. This is just, calculus, gymnastics. But we end up with a valid expression here, and We can knock out these r to the minus n's if we want to. We just have to be able to find some value of r where our expression is valid, right? And then it works out. So this is basically just, again, it's the generalization of the IDTFT, but now expressed in terms of z, in terms of a loop on the z-plane. Which means that, on the z-plane, we're finding some set of values. I don't know, why is it counterclockwise? I'm not sure why it's counterclockwise, but we're finding some set of values we're evaluating the integral along that circle there. And as long as we're inside the region of convergence, then the values are all valid and we're okay. Turns out there's the Cauchy residue theorem that if you want to find out the, well, I don't really know what this means. But there is this thing that you say, there's this notion of residues, which are the values of the function on the poles, where it's actually infinite, but you can calculate the residues, and so you can calculate an individual value of g of n by doing a manipulation of that, by basically shifting your g of your function so that the value you're trying to get is the value for z equals at time 0, and then you can evaluate this, and you get the value, the overall value as the particular sample value. The bottom line here is, yes, there exists, the rigorous mathematical things which do indeed generalize the IDTFT, but by this point, it's the math becomes a little bit too much for me anyway, and so we're not going to pursue that technique. If you're very, very comfortable with this kind of manipulation, calculus manipulation, then this is a good approach. But in general, that's a bit much for us engineers. So let's go on to the second way of doing it. And this is this idea of identifying individual coefficients of the polynomial, the implicit polynomial in z that is defined by z transform, right? So we said one way of thinking about what's going on is we're defining a function of z, which is just a polynomial with a lot of different coefficients. Each of the coefficients is a value of g of n, the time sequence we're trying to recover. If we have a g of z which is right-sided, meaning that we know that it's 0 for before some value of n, and then it's only non-zero after that value of n, and it's expressed as a rational polynomial, so we've got g of z in a closed form where we've got two finite order polynomials, but they're in a ratio. It can't directly read off the individual values of z. These things will be polynomials in z. They'll have coefficients, but they're not in this form. They're not just simply a full power series expression. But we can get that full in general infinite length power series expression by actually working through the division, and this is basically the generalization of how we do long division of numbers that we learned in grade school. So the procedure is you express your numerator and denominator in descending powers of z, assuming that you are working causally. You're trying to find a solution that has a right-sided expansion. You look at the highest terms. You figure out what constant you're going to need to cancel out the highest terms in z from the denominator using the numerator, or whichever way around it is, sorry. You subtract that and you repeat. You cancel out leading terms, then you get something else for the remaining terms, and then you go to a higher or a higher power of z to the minus 1 to get the next term to come out. So it's easiest to explain with an example. So here's our h of z. H of z is 1 plus 2z to the minus 1 on 1 plus 0.4z to the minus 1 minus 0.12z to the minus 2. Okay? So we've got an h of z a closed form expression within the region of convergence. That is the ratio of two polynomials, a first-order numerator and a second-order denominator, meaning it has a single 0. The 0 is at z equal minus 2, has a couple of poles at whatever the roots of this quadratic are. Okay. So we're going to do this division as if it was as if these were not powers of z, but were just digits in a 10, in a power of 10, in decimal expression, decimal number. So here's the denominator. We're dividing the denominator into the numerator. We're arranging them in the descending powers of z. So we start off with the highest power, z to the 0, z to the minus 1, z to the minus 2, z to the 0, z to the minus 1. There's no z to the minus 2. OK, so now we're going to try and cancel the highest power that we've got. The highest one is the z to the 0, which is 1. In order to cancel that, we're going to have to take 1 times this. So we get a 1 up here, and then we write down 1 times this whole thing down here, and we subtract it out. Right? So 1 minus 1 gives us 0, which was, the whole point. 2, z to the minus 1, minus 0.4 z to the minus 1 leaves us with 1.6 z to the minus 1. And then nothing, z to the minus 2, minus 0.12 z to the minus 2 gives us plus 0.12 z to the minus 2. So this is our remainder. So now to get the second term of our expression, we figure out what we're going to have to multiply this by to cancel the leading term here. Because we've got a 1 here, the answer is always just whatever this leading term is. So we have the second term, 1.6 z to the minus 1. That's the second term in our result. But then we multiply this by it to get what we're going to have to subtract off. So 1.6 z to the minus 1 times 1, 1.6 z to the minus 1, 1.6 z to the minus 1 times plus 0.4 z to the minus 1 is 1.6 times 0.4, 0.64 z to the minus 2. 1.6 z to the minus 1 times minus 0.12 z to the minus 2 gives us minus 0.192 z to the minus 3. Subtract that from our remainder. The leading term cancels out. 0.12 minus 0.64 gives us negative 0.52. 0 minus 0.192 gives us plus 0.192 z to the minus 3. Here's our remainder. Again, we're going to have to figure out what we're going to have to use to cancel this, which will be this again in this case. If it wasn't a 1 out here, if it was like a 2 or a z, it would be something different. But in this case, it's just the same thing. And we can repeat, right? So you see what I'm doing? It reminds you of long division by hand, right? And it's kind of interesting because when you learn long division, my son is 11. He's in 6th grade, and he's doing this, right? They're teaching him how to do long division. And it's like, oh, wait, no, this is not just a routine that you just turn a crank. If you think about it as this decimal number is actually a polynomial in 10, right? 10 to the 0, 10 to the 1, 10 to 2. Then it's all the same thing. It sort of seems like a more satisfying thing. But anyway, we're familiar with the procedure, and we can see that, yes, it's going to successfully give us this thing, which now you see in the same way that when we did long division, we ended up with recurring decimals, right? We know that sometimes you never get rid of everything. It keeps recurring. So here you can see that this is going to give us potentially, we may never get rid of the residual here, so we may have a non-ending sequence of powers of z coming out. And so that's the point. We started off with a finite order rational polynomial. We ended up with an infinite order straight up polynomial. They're the same thing, right? We've just done the expression. So for any value of z, if you plug it into this, like z equal 3, you get some value out. If you plug z equal 3 into this, there are a lot of terms here, but in theory, if I guess z equal 3 would work, right? Because we're going to raise it to successively large negative powers, so they would tend to disappear. It would converge to the same result. We get the same answer. It's just that one is expressed in a nice closed form and one is an infinite series. So this one's clearly much more useful to work with in terms of writing it down. But this one has the advantage that now if you say, well, I want this happens to correspond to sum of h of n, z to the minus n, I can just look for a particular value of z to the minus n. I can read off the hn that comes with it. And that's what we're trying to do when we're trying to do the inverse Z transform. So, you could, if someone gives you this and says, what is the value of h of 3, little h of n for n equal 3, that this Z transform corresponds to, as long as they gave you the region of convergence. So they tell you the region of convergence, and you'd say, oh, okay, it's the outside of some circle, therefore we're talking about the right-sided version. And then you know that you're looking for a solution like this that starts at some power and then goes into increasing negative powers. As long as you did that, you could then just do this up to whatever value you wanted, and then you'd have the value you needed. If they gave you something like this and told you the region of convergence was the interior, then you you could do this whole long division thing in terms of ascending powers of Z, and that you'd end up with 1 plus something Z plus something Z squared, which would correspond to values of n going leftwards in time, right? The thing would work, but you'd have to set it up differently, so you got an answer that was in terms of different set of values of Z. If they told you that it had a region of convergence which was the intersection, so it meant that it was both left-sided and right-sided, then I don't think we'd be able to use this technique. I don't know. I guess the way you try and do it would be to break it up into two Z transform terms, one that was right-sided, one that was left-sided, and you could solve each of these for that. There should be a way to do it, right? Just thinking logically that what the answer is going to be. It's going to be two different terms. And if it's an intersection, it means that it's the sum of two closed form expressions, one of which has a certain region of convergence, the other which has a different one. So you should be able to identify those and figure it out. But in general, you'd have to do extra work to make it work. But we almost always want to talk about causal systems, systems which nothing happens until you put a signal in, then something happens, which means they're going to be right-sided like this, and so this is the case we care about. Okay? Okay, so the third way, the partial fractions way, this is sort of, again, a novel piece of mathematics that we're introducing. And it's sort of, like I say, the main point of doing it is just that it actually turns out to be practical in real homework question type situations. So someone gives us, again, a Z transform expressed as a rational polynomial. Now, the rational polynomial is not something which we can directly identify with our Z transform identities, unless it's a very, very simple one that happens to be in the table. But typically, it will be the product of various poles and various zeros, because that's the most, in terms of understanding the shape of the Z transform surface and the Fourier transform, that's the way we like to think about it. But if we could see it as the sum of various components, then we know that Z transform is linear, so if we can do the inverse Z transform of each component in a sum, and then we can add them together in the inverse domain, in the time domain, and we'll get the right answer. So if we can just algebraically manipulate our Z transform expression to make it in terms of the sums of various pieces that we can directly just look up on our Z transform identity table, then we're done. And so most often what we're thinking about is these kinds of terms, alpha to the mu of n, whose Z transform is 1 over 1 minus alpha Z to the minus 1, or some linear version of that. If we can find those, we can just directly solve the problem. But here's the thing, right? Normally the Z transform we're given is expressed in terms of a denominator which is maybe a single polynomial in Z, which we can then think about factoring into a set of first-order polynomials, first-order expressions like this. But what we want is not a denominator that's a product of terms, but a set of discrete different denominators which are each individual first-order terms like this. Well, it turns out I'd never had to do this before, this particular problem, but it's a perfectly well-formed and nice mathematical problem, we can see that by looking at it the other way around. If someone gave you this thing, which was a sum of 3 simple fractions like this, and then said, put it over a common denominator, you'd know what to do. You'd say, well, a common denominator would be the product of these 3 denominators. And then so here's our common denominator. And then to get the different numerators, which are going to sum together, well, this thing, to put it over the common denominator, we'd multiply top and bottom by these 2 terms. So we'd end up with a times the other 2 terms. And then this one would be b times the other 2 terms, and this one would be c times the other 2 terms. So we know that there is an equivalence between some function over the product of these 3 denominator terms and some expression that has each of these denominator factors as a separate term and a sum. Going forwards is easy. All we have to do is now go from the sort of simplified form of this to find this part back. So we're trying to go from some polynomial in z divided by a denominator that's a product of simple factors like this to a sum of individual fractions where the denominator is one of the factors and then some constant on top. And the constants are what we have to find. In general, notice here that the denominator is going to be 3rd order, but each of these numerator terms is 2nd order because there's one, in this kind of situation, there's one less z in the numerator than the denominator. Obviously, each of these would be a 2nd order term, so we'd end up with 3 numbers on the top when we add those all things together. So to do this, we want to have the numerator be a lower order than the denominator because we want to get we don't want to get any function z. We want this to be basically 1 over 1 minus alpha z to the minus 1 because then we can write it down. But it's going to be some constant with some particular lambda in there. So, but we can always do that because we can cancel out some of the terms of our numerator by doing long division. We can just say, okay, well, if we've got an extra z to the, if we've got the leading term in the numerator is too large, then we can just say, well, we can do the first couple of stages of long division until our residual is just the part that has the lower order. And then we're left with a constant plus a fraction. Again, it's not worth worrying about too much. Just know that there's no problem with solving that problem. Okay, so here's the basic problem we're trying to solve. To say that if f of z is p of z divided by this product of factors, we want to find the row sub L's that express this as a sum of simple terms. Once we've found those, then each of these terms we can directly write down the inverse Z transform. It's just lambda sub L to the n mu of n times rho of L. And so once we had this, then the final part of the inverse Z transform problem is trivial. So basically the only problem we have left is finding the rows. And this is the partial fractions technique, which is that you basically evaluate the full expression at each value that would be one of the poles after taking out that factor that would make it a pole. And so sometimes, the way you think about this is you have your expression with a set of denominators. You cover up each one, and then you evaluate the expression to get the value of the expression at the root to get the actual value of rho for that term in the final sum. And again, this is something that I was taught as this is how you do it. It's pretty straightforward. Just remember the recipe. But that stuff bugs me. So, but because well, why does it work? So it turns out this is actually I think this is neat. We've got these 2 expressions. It's a case of, they're the same, they give you the same value. By construction, our requirement is that they're the same function, just different ways of expressing that function. So for any value of z, they give you the same result. But it has poles, right? This is a z function with poles. It's got those particular values of z where it shoots up to infinity. We want both of these things to be infinity at that point. That'll work because this thing will have, you know, one of the terms in its denominator will go to 0, so the whole thing will be something divided by 0. Here, there'll be a bunch of sums. Most of the sums will be well behaved, but one of them will be a something divided by 0, so it'll shoot off to 0. The way to understand this is that as we get close to the pole, the term that's relevant to that pole is much larger than all the other terms, so it's dominating. And basically, we can forget about the other terms. The only problem is that the value, so that means that if we can evaluate the value at that pole, then just this one term in the sum is the dominant term, and we don't have to worry about the fact that we ignored the other terms. We can basically sort of read off the value of rho, and the other rows, rho sub L, the other rows won't matter. So we just have to evaluate this at the pole, but of course it's a pole, so when we evaluate it, it goes to infinity. But if we evaluate the value of that pole scaled down a lot so that it's no longer infinity when we try and look at it, then we just get this thing that we wanted. So we want to evaluate this at a pole, but scaled down in such a way that it becomes finite. Well, the reason it's a pole is because we are dividing by this. So if we multiply by this, then it'll suddenly be well behaved. It'll be, I think, that's what's meant by a residue. And so that's what we do. We just take this expression, we multiply by this term, which means basically we just cancel it out of the denominator. Then we evaluate it, and that gives us this thing, which is the value of the particular term in the sum. You could think about it, what happens. I mean, you know, we don't like to think of, when we multiply by 0 and divide by 0, things get weird. Think about z very close to lambda. So everything's finite now, but it's just very, very large. This thing has got a denominator which is very small, so it has some large value. This thing has also got a denominator that's very small, so it's rho L times 1 over epsilon. We've still got this term being much, much larger than all the other terms, right? All the other terms are 1 over 3, 1 over 7.5. This one's 1 over epsilon, so it's huge, 10 to the 200 or something. And then we've got, okay, this is rho times 10 to the 200. We can evaluate what this thing is. We scale down by the 10 to the minus 200, we get rho out. That's all that's going on. So it sort of, I kind of like that, you know, at the poles, the fact that you get, in one expression, you're getting poles by summing separate functions that have separate poles. On the other side, you've got some expression where all the poles kind of come out of the expression at once. At the poles, the fact that you don't really worry about the difference between those two, and you can equate them. If that didn't make sense to you, it doesn't matter at all. It was just that if you were curious about why this worked, that's kind of my insight into how it does work. I'm now much happier with this whole approach. So again, for the practical consequence of this, let's just go through doing an example here. So here's our h of z, which is actually the same one we did in long division. 1 plus 2z to the minus 1 over 1 plus 0.4z to the minus 1 minus 0.12z to the minus 2. Our partial fractions goal is to say, well, we're going to express this denominator in terms of its roots, which turn out to be 0.6 and minus 0.2. Check. We sum those. They give us 0.4. We multiply those. They give us minus 0.12. OK, so they are indeed the roots. If we expanded out this, we'd get that. So we've got this expression in terms of a rational polynomial in z with a factored denominator. And we want to express it as the sum of two terms for each of the factors of the denominator. And then the partial fractions thing says, OK, to find rho 1, we look at this root here, which is z equal minus 0.6, right? So this term would go to 0. So then we look at this. We take out the term that would be the pole, and we evaluate the rest of it at z equal minus 0.6. So we get 1 plus 2 divided by minus 0.6 on 1 minus 0.2 divided by minus 0.6, which when we evaluate it through gives us minus 1.75. And then that's a numerator here to get a numerator here. We do the same thing at z equal 0.2 with this term removed. We get this, and this is 2.75. So that gives us this sum, this individual sum of terms, that rho 1 divided by 1 plus lambda 1 z to the minus 1, and rho 2 divided by minus lambda 2 z to the minus 1. Again, of course, to solve this expression here is equal to this expression for all values of z, right? This is just some polynomial, rational polynomial in z, and we've unconditionally we can say, well, it's equal to this. Now, if you're telling us that rational polynomial in z is the z transform of a particular function, okay, but you have to tell us what the region of convergence is, so we know where which of the possible functions, which parts of the surface it's describing. So, okay, we're told the region of convergence is the exterior of some circle. In particular, it's going to be the circle that has that doesn't include any of the poles, because the poles can never lie in the region of convergence. So if we know it's the exterior of some circle, then we know it's a right-sided sequence, and so then we can just write down the inversely transforms of these two, as this is, some constant times 1 minus lambda z to the minus 1. So it's just lambda to the n, mu of n times the constant. And then this one similarly gives us lambda as 0.2 to the n. The constant is 2.75 times mu of n. So this is our now closed form expression for h of n, which assumes that n is 0 which implicitly has the case that n was 0, h was 0 for n less than 0. But now we can work that out. So here's minus 0.6 to the n for n equals 0, 1, 2, 3. 0.2 to the n for n equals 0, 1, 2, 3. Here are two constants. When we add those up, we get these values, 1, 1.6 minus 0.52, 0.4. If we go back to our long division thing, 1, 1.6 minus 0.52, 0.4. So it gives us it does indeed work, gives us the right answer. And of course, the advantage here is if I wanted to know the value for n equal 100, in long division, I'd have to work out all the intermediate stages until I got down to the remainder with the z to the minus 100 term in. Here, I just solve the closed form solution, and I can just plug in any value of n and get the answer out. It's also, it's kind of interesting to see how these things emerge, but and it's nice that it does work out. Any questions? Okay, so we've seen the Z transform. I've tried to explain to you why we care about it, because its relation to the Fourier transform. And for completeness, we've seen how to go back from the Z transform to the time domain, which needed to be possible. In the Fourier transform, there are situations where you're thinking about some signal, some system, you end up with a Fourier transform, you want to know what it is in the time domain, you actually need to do an inverse Fourier transform, most often an IDFT, because that's the one you can calculate in MATLAB. In the Z transform, I've never had a situation where I've actually wanted to do one of these for real, full up. It's always been like, no, I only care about this because I can get its Fourier transform, and then I just do the inverse of the Fourier transform. But I'm sure other people have. Okay. So now we can go on to topic 5. And at this point, the boundaries between the topics is a little bit arbitrary, because basically this is continuous sequence. But now we're going to really work the idea of this relationship between the Fourier transform and the Z transform, and in particular this idea that knowing the locations of the poles and zeros gives us information about the Z transform, about the Fourier transform. So we're going to have to introduce these specific concepts of frequency response and transfer function. But they're basically just names for things that we've already thought about. So when we're looking at the Fourier transform, we have this basic idea that the Fourier transform x of e to j omega tells you the weight of different sinusoidal components, e to the j omega n, contributing to x of n. Right? This is an integral, but an integral is just a sum over a very large number of individual little pieces. And so as a function of omega, x of e to the j omega tells you the magnitude and phase of that particular sinusoid, e to the j omega n, that contributes to x of n. If x of n is a sinusoid, x of e to the j omega is a couple of delta functions, so it literally works, the integral turns into a sum. For finite length x of n, x of e to the j omega is actually going to not be a delta function. It's going to be some distribution over frequencies, but it's still, the intuitions work the same. It's saying, well, there's a little bit of each of these individual frequencies present in x of n. This is like the whole point of Fourier analysis, which is that if we have, well, the point is that not only can we express x of n in terms of these sinusoidal bases, but when we do convolution, all we end up doing is scaling these individual ones, scaling them by the magnitudes of the Fourier transform of the system, the impulse response that we're convolving by. And that's this idea of eigenfunctions, that if you have a signal which is a sum of individual sinusoids, then the output of, putting it through this transformation is that, well, each of the eigenfunctions is just scaled. It's not, we're only going to get the ones out that we put in. And this is because these sinusoids are the eigenfunctions of linear shift invariant systems, the systems that we can characterize by their Fourier transform. So we can understand what a system is going to do in those terms simply by saying, well, this system takes the frequency component, the sinusoid at 1,000 hertz, and scales it by some amplitude and by some phase shift. But that's all it does. And if we know that, then we know everything about the system because we can predict the output of the system for any input simply by using, by thinking about it in the Fourier domain. So that's what the frequency response is. It's just that description of the modification of the phase and the magnitude of each frequency component as a way of describing a system. Let's just examine this idea of eigenfunctions mathematically, because I've sort of said it and I've sort of waved my hands a little, but let's just make sure it works out mathematically. So if we have a system, we can describe that system completely by its impulse response h of n. And what that means is if we put a signal x of n into the system, we get an output y of n, which is the convolution of x of n and h of n. Right? That's our basic linear shift invariant convolution behavior. We can write out the convolution sum explicitly like this. Just means for some particular value of n, we sum over all values of h multiplied by x of n at that particular time previous, sum them up, and we get the output. Now, if we're putting a sinusoid in this case we're going to use a complex sinusoid because mathematically it's easiest. So if x of n is equal to e to the j omega 0 n, so this is some specific constant value of omega, then y of n is simply that convolution. So here we write that down, but we substitute e to the j omega n for x of n, or in this case e to the j omega 0 n minus m for x of n minus m. And then we can rearrange this. We can break this into two terms, e to the j omega 0 n and e to the minus j omega 0 m. Put this one in here. Have this one left out at the end. This sum over m, h of m, e to the minus j omega 0 m, we recognize as the dTft of h of n, or big H of e to the j omega 0. If it were just omega of the dTft, it's the dTft at a particular value, omega 0, h of e to the j omega 0. And this, of course, is just x of n again. So we can just write that down like this. And so we're saying when x of n is a sinusoid at some specific frequency, the output y of n is just the value of the DTFT of the impulse response at that frequency times the input, which was the original sinusoid. So we can write it like this. It's the magnitude of h of e to the j omega times e to the j omega n plus phase of h of e to the j omega. And so that's what eigenfunction means, right? That we put one of these eigenfunctions in. All we got out was the same eigenfunction scaled by some constant, complex constant here. And in particular, our eigenvalues here are the values of the Fourier transform of the impulse response. So in words, if x of n is a complex sinusoid at omega 0, frequency omega 0, then the output of a system with impulse response h of n is the same sinusoid, but scaled by the magnitude of h of e to the j omega 0, the DTFT of the impulse response at omega 0, and phase shifted by the angle of h of e to the j omega 0, which we're writing as theta of omega 0 here, where h of e to the j omega is just the DTFT. And because we can take any signal and we can break it down into individual sinusoids, that's what Fourier analysis does, then we can, this generalizes to any signal, not just individual complex sinusoids. So then we can talk about the magnitude of h of e to the j omega 0 as the magnitude response. It's the gain, the amplification that any single sinusoid will experience when passed through the system, and the arg of e to the j omega 0, the angle of that complex function, as the phase response, which is the phase shift any particular sinusoid will experience when passed through the system. Of course, we're still talking about complex sinusoids, which are not the sinusoids we're used to seeing in our circuits, but we know we can build a real sinusoid as the sum of two complex sinusoids, complex conjugate sinusoids. Let's just check that this idea of magnitude response and phase response does work even for a real sinusoid. So if we have a sinusoid x of n is equal to cosine omega 0 n with, say, a gain here of a and a phase relative to cosine of phi. Here it is expressed as the sum of the two complex sinusoids, conjugate complex sinusoids, e to the j omega 0 n plus phi and e to the minus j omega 0 n plus phi. By Euler's equation, this is cos plus j sine, cos minus j sine. So the j sine parts cancel out when we add them up. We get 2 cos, so we divide a on 2 to get that. This has to be equal to the I dTFT, right? The integral of x of e to the j omega, e to the j omega, n d omega. So that means that x of e to the j omega has to consist of two delta functions at these two values of omega, omega 0 and minus omega 0. So this, and the weights are going to be a on 2. So this is like just, by inspection, this is what the Fourier transform, the DTFT of this real sinusoid looks like. And it's almost just a complex sinusoid, but it has the conjugate there as well. Right? So now, well, we just worked out that if we put in one of these e to the j omega 0 n's, then the output is going to be the magnitude, the value of the DTFT at that omega 0, h of e to the j omega 0 times that omega 0 n. We've got these extra terms coming out here, the e to the j phi phase shift and the a on 2 scaling function, but it's just linear, so that thing just carries through. So we get this one for the positive frequency component, this one for the negative frequency component, the minus omega 0 part. Assuming that we've got a system whose impulse response is real, which is something we would know, right, if we had a real circuit where there were no imaginary voltages involved, then we know that h of e to the j omega is going to be complex conjugate, right? That's the constraint we had. If you have a real signal, then because the IDTFT has got to have the imaginary parts cancel it for every frequency, the DTFT itself has got to be complex conjugate. So then h of minus e to the j omega is going to be just h of e to the j omega times e to the minus j phase of that. So then we can write down both of these terms in terms of h of e to the plus j omega, and we can reapply Euler's formula. We get back into real terms, and lo and behold, we get what we expected, which is the input cosine, same frequency. The phase has been further shifted by the phase of the impulse response at omega 0, and the gain has been further modified by the magnitude of the DTFT of the impulse response at omega 0. So that's the same, it's the same result. It's what we had in words on the previous slide. We're just showing that because of the way it affects both the positive and negative frequencies, and for a complex conjugate DTFT, which is the DTFT of a real impulse response, we get exactly the same behavior. So here's the picture, sinusoid going in, sinusoid coming out, a real sinusoid with frequency omega 0, passed through a linear shift invariant system with a real impulse response, has its gain modified by magnitude of h of e to the j omega 0, the magnitude response value at omega 0, and its phase shifted by theta of omega 0, the phase response value at omega 0. I'm hoping that is just sort of trying to formalize something that we already basically understood. This is kind of the point about the Fourier transform and, convolution becoming multiplication in the Fourier domain. So that's fine, and that's the good solid basis of our intuitions about what the Fourier transform does. Now, the problem with that is we're still talking about the full-up Fourier transform, which is expressing x in terms of e to the j omega n for all n. These are infinite duration sinusoids, which, is again something that we don't encounter, or we'll never know. We're never around for long enough to know if our sinusoid is going to exist forever. So, in particular, it means it has to have existed from the beginning of time, from n equal negative infinity. So what happens if we actually have signals which are sinusoids, but they're gated? They start at some particular time. Let's not worry about what happens in the future, but even the fact that there's something that's happened in the past which may not have been under our control. So if we have x of n equal to e to j omega 0 n mu of n, so it starts at time 0 and it's 0 before that, that's clearly going to affect the output y of n. What's mathematically the impact? So again, y of n is equal to h convolved with x, which is a sum over all m, say, of h of m times x of n minus m. Well, if we know that x involves mu of n, multiplied by mu of n, then we know that x of n minus m is going to be 0 for m larger than m, because that's when we'll get mu of some negative number coming in. So basically, whereas before, without this, it would just be this sum from m equals minus infinity to infinity, h of m, e to the j omega 0 n minus m. That was the expression we had a couple of slides back. Now what's happened is we've got an upper limit on our summation here, that we only look backwards for a particular value of n at the output. We can only look backwards in our h up to the point where x begins. There are different ways of expressing this depending on which version of the convolution sum you come up with. But basically what happens is that because this is 0 over some range, this inner product here now has a limited range that we apply it to. By looking at it this way, we can sort of write it in terms of completing the sum. So we can say, well, if only we had this set of points from m equal n plus 1 to infinity, then we just have the full-up Fourier transform here. So we can write this in terms of what it would have been if x hadn't been gated, the summation we had without the mu term, minus the bits we had to add on, which is this, the sum from m equal n plus 1 to infinity, h of m e to the j omega 0 n minus n. And so this part we recognize as just being the h of e to the j omega 0 e to the j omega 0 n, the steady state response, what y would be if x was that sinusoid over all time. So our output is almost this, but it has this correction term. And this is the part that arises because we have an x that's gated with time. So we call it the transient response because it's the bit that is different because x was transient. X changed at some point. Okay, so let's see what that mathematically that looks a little bit obscure at the moment. Let's see exactly what it is. So here it is. Here's this expression again. Here's the part that we just had, the transient response. The sum from m equal n plus 1 to infinity of h of m e to the j omega 0 m. And now if we think about this as a function of n, what we're saying is, well, for each value, for each time n, we've still got the same kind of sinusoidal basis here, but it's a scaling factor applied to that sinusoidal basis. And what this is actually the Fourier transform of h of m starting from point n minus 1. So if we have an impulse response that's got some set of points, if we started from 0, we just have the regular Fourier transform. But if we start from some larger value, it's like we've chopped off, we've zeroed out the first n values of that impulse response, and we're just taking the Fourier transform with the remainder. And then that's the gain that we're applying to our sinusoid that we're going to subtract off from the steady state response. So clearly when n equals, for h that's causal, so if h is non-zero only for n greater than 0, for n equal to 0 or n equal minus 1, this is going to be just this term. And so we'll get no output, which is kind of what we'd expect. If we've got an input that only starts at time 0, we expect no output for time less than 0. But for times greater than 0, we're going to subtract some stuff off. But as we sort of get further and further in, we're using, if we have some h of m that decays away with time, we're getting less and less here. And so this transient term dies away. So here's a plot. This blue curve is this part, the steady state response, h of e to the j omega 0 times e to the j omega 0 n. This red part is the transient response. This is for some particular, I haven't told you what h of n is, but it's some nice decaying impulse response here. So here's the transient response, which actually I've sort of plotted it starting at 0, but actually it's sort of, it's equal to the negative of the steady state response for time less than 0 if we bother to calculate it there. And the green is the actual system output, which is basically the green minus the red gives us the blue, or the blue plus the red gives us the green. And so what we're seeing here is that by virtue of this being a signal that turns on at some particular time, what we actually get is the green. What the Fourier transform view would lead us to expect is the blue. For times close to 0, there's a significant deviation between the two. But as we go on, they become the same. And so this is this idea that there's a transient response, but it dies away. And so as long as we're not too close to the transient, we can think about this signal x of n, this sinusoid times mu of n. We can just imagine it. We can just forget about the mu of n. And provided we're far enough away from the transient in terms of the length of the impulse response of our system, then there's not going to be that much difference. This property where the impulse response dies away with time, that's normally the kind of thing we're talking about, that if we have a system that's sort of stable, which means that you put some energy in, it does some stuff, but then it sort of settles back down again, then that's that definition, that the impulse response will get smaller the further away you are from zero, and so the transient response will die away as you move away from the transient into the steady state region. Again, this is not something. This is just, we have to recognize that there was this kind of disconnect between this pure Fourier domain thinking, where we're talking about signals being composed of these infinite duration sinusoids, and the practical situation we normally deal with, which is signals that start at particular times. This is just sort of the sketch of why, okay, we're using this simplification to think about them as infinite duration sinusoids, but most of the time it doesn't mess us up too much. Any questions? Okay, so now let's look at using the frequency response to actually understand and characterize the behavior of a system. So here's an example, and for example, we're going to use our moving average filter again. This is our moving average filter, which we introduced when we started talking about time domain operations, that the output y of n is the sum of x of n minus L for L equals 0 to n minus 1. So it's the sum of the current, the most recent m points. It's the average of them, 1 over m. We thought about this as taking moving average, but we can understand this as convolution, that this is just, this would be a convolution sum with h of L, where h of L is equal to 1 over m for these values of L and 0 everywhere else. So y of n is simply x of n convolved with h of n for this h of n, where it's got m values, m non-zero values of 1 over m, and it's 0 everywhere else. So if that's true, then the frequency response to this system is just given by our DTFT. So we can take the DTFT of this. The DTFT is simply the sum over all n of h of n e to the minus j omega n. In this case, h of n is 1 over m for these values of n and 0 everywhere else. So what we end up with now is a finite geometric series, some finite geometric sum, which we solved before. This is the identity for the finite geometric sum. You scale it over by 1 point, then subtract them, and then divide through by the two things. I hope you know what I mean. So this is the expression we get. And then this is this case which we looked at before, where we can think of these as two complex phasors that are sort of equally split around their geometric average, their geometric mean, which then gives us, if we take out half of this, we get e to the plus j omega m on 2 minus e to the minus j omega m on 2, all times e to the j omega m on 2. But e to the plus j omega m on 2 minus e to the minus j omega m on 2 is minus 2j sine m omega on 2. So, and we do this for the top and the bottom. We take those terms we factored out here, and then we end up with this sine m omega on 2 on sine omega on 2, this so-called periodic sinc function that we saw before. So we end up with a nice closed form expression for the Fourier transform, the DTFT, of this impulse response of this system in terms of a scalar constant, a phasor constant, right? This is a linear phase term. It's just e to the j omega times some value here, which is just some constant value. So it's the phase is omega. It's a phase rotation of minus omega m minus 1 on 2. So it increases with frequency, but it's linear in frequency. And then this function here, which is again a real scalar function of omega, which is our magnitude response. So here's that expression again, and here's actually plotting it to see what it does for m equal 5. So this is actually sine m omega on 2 divided by sine omega on 2 for m equal 5 for omega equals minus 2 pi to 2 pi, right? So it's that's the period of the underlying thing. So sine of omega on 2 looks like this. Sine of 5 omega on 2 has 5 of those in it. When we divide them, we get this out, which is our, looks like our periodic sink. It has a maxima at 0, has some ripples, then it's periodic in this case in omega equals, well, it turns out to be periodic in omega equals 2 pi because of the symmetry of those two. Now, if you want to know what the magnitude and the phase response is, we have to take, the magnitude of this is going to be this thing rectified. So here's the magnitude. Because the magnitude of this is always 1. There's a 1 over m term in here, which just scales the whole, the y-axis. The phase here, I said this was a linear phase term, which would be a straight line. Of course, when we rectified this, we ended up basically, this thing goes positive and negative. So the overall phase is this, continuous value in frequency plus the pi phase shift corresponding to the flip of sine of this. So here's the phase function. It's nice and linear, but then every time this goes through 0, it has a jump of pi radians, which gives us this little jagged sawtooth thing going on. We often see sawtooths in phase functions because, of course, they're limited to the principal values between minus pi and pi. But here, it's not a jump that's because we're going from, we're going below negative pi. It's just a jump that comes from this sine flip. So it's a pi-sized jump, and it occurs at various different values. But this now is basically this is a full and complete magnitude and phase description of the DTFT. So this is our magnitude response. This is our phase response. And what the frequency response concept is telling us, if we put in a signal which is composed of some set of sinusoids, some sum of individual sinusoids, then we can figure out what the output is going to be. Oh my goodness, sorry, I didn't realize I'd ever run out of time. We can figure out what the output is going to be simply by looking at the magnitude and phase of each of these components. So let me just show you this last slide. So here's the magnitude and phase response. Here are the two components. To figure out the output, we just say, OK, well, give me the particular frequency. I'll look in my magnitude and phase, look them up, and then I expect that I know I can get the approximate value of the frequency response, so the output is just going to be each of these components scaled by these two gains. And so next time we'll look at just doing that in practice and seeing that it really does work out the way we expect. Any questions? All right, see you on Monday.